Thank you. Yeah. Okay, so look at this cover, and you see those are future engineers and managers in construction, and then they will be enabled to see further and to get to the point by artificial intelligence. Okay, but today, and I will talk a little bit more. I will focus on the fundamental problem. Okay, and how we can define a fully fledged problem statement, based on the industry practice, and in the context of planning and scheduling, bridge girder fabrication. Okay, so give you a little bit introduction. Okay, these are typical highway bridges. Okay, some are jargon, some terminology. The steel girder consists of a flange, actually two flanges and the one web. So the steel undergirds the bridge. Okay. So here's another schematic view just of the girder line. So each line is consisting of several girders, and pay attention to the connection details. Okay. So we call the field splice. So they are well prepared, fabricated in the fabrication shop to make sure they will be connected in place at the construction site later. Okay. One shot of the final product out of a typical steel fabrication shop. Okay. This is one girder. Okay. It could be as long as 30 meters or 50 meters, and a lot of fabrication features just to ensure the field installation, also the connections will be properly completed in the field. Okay. The challenges for the current practice in structural steel girder fabrication are identified here. Okay. Each girder looks alike, but there are a lot of variations. So every girder is custom built to individual bridges. They're made to order. Okay. And then the product sequencing is the key. Okay. These are not small stuff. They're heavy, they're bulky, and how to sequence the girder lines, the different bridges, and then once they're loaded to the fabrication shop, it will be very difficult to make changes to the sequence production order. And also the site client really demands lean performance. So too early delivery to the site is not acceptable. There's no laydown yard. And too late delivery to the site, it would cause the field crew idling again. That's even worse. So in the fabrication shop itself, they employ very expensive specialist trades like welders, those kind of iron workers. Okay? So by all means, the shop manager must avoid idling such kind of resources. Okay? Based on our finding, there's no cost-effective analytical tool being used for the production planning in a typical shop in Canada, in North America. So here, just give you a very general work breakdown from the eyes of project manager. Okay, this could be done by you, by any engineering student. Okay, so it's not very complicated. Okay, and this here is a typical activity on node network representation. You see all the components, all the activities, and they're logically connected by those arrows. Okay. And some activities can be repeated depending on the features of the girder. Some activities may not happen at all, and also depending on the girder features. Okay. And then if you think about the resource links, or the limited crane availability, the limited trays availability, you have to add a lot of such kind of arrows. So all of a sudden, the network becomes messy. Okay, so here is an illustration of the detail complexity. The calculation of total number of activities in your AON network, in your P6 model, could be tens of thousands, very quickly. And then the relationships between them in the network could be even more, could be hundreds of thousands, okay? I'm sorry, yeah. So let's look at the fabrication shop from the eyes of the shop superintendent, okay? So at this part, I will just walk through very quickly. Those are a lot of fitting, a lot of welding, a lot of those kind of details, drilling holes. These are the field splice, okay? And then these are for some stiffeners, okay? And those are the studs. And this is a final product, okay? It's a huge, it's a heavy, and the shop manager, who is an experienced, call it commander-in-chief in this real battlefield, help us break down all the work. Even to fabricate one girder, it could take almost 90, 100 steps or tasks, okay? I'll just give you one example, and you have to account for those details, just to connect two pieces, okay? So there are a lot of plates, holes to be made in the shop. For the field splashing, you have to do some trial assembly in the field, in the shop, sorry. But look at the setting in the shop, okay? Very crowded. There's some gantry crane moving on top, and then, okay, so here are some kind of animation, okay? So for some girders needs to be spliced just on one end, and it will be placed in the shop and taking the space and waiting for the adjacent girder to be ready, and then they'll do a trial assembly and make sure all the holes, all the plates would fit, okay? So for this girder in the middle, G1B, and it takes splicing, drilling holes on the two ends, okay? And then once it is done, the adjacent girder will be, G1A will be kind of moved in, okay? So this sequence is dictated by the technology, is dictated by the resources available. Also, it's very difficult to change because of the size, because of the weight of the products, okay? I think that even the company has invested in some lean technology, and this value stream mapping has been done for one girder, only one girder, okay? It just, I don't want you to see the detail. It's overwhelmingly complex, still doesn't yet help making better decisions, okay? So I come to this slide. It makes some strong statements here, okay? So all the models we have been using are wrong. They don't work in this context, okay? On behalf of the shop superintendent. So the CPM, the P6, repetitive scheduling, the VSM, they don't work. So the commercial simulation tool, they don't work, okay? So I said that this is the question, okay? So the solution is there are two options, okay? So you can take a quick read of this cartoon. So we're very lucky to have the trust of the industry partner, and we take the second option, okay? Let's try something new. And we can't be sure it will work, okay? There's some risk, but that actually creates the research opportunity and the collaboration opportunity between industry and academia, okay? So this is actually some methodology framework, application framework. We just try to break down the complexity into tiers, okay? Into layers or tiers. Here, just the bottom, middle, and the top, okay? So at the bottom are those events that never change. Those are in the middle, and they just require occasional change. And at the top, that's for the interface with the manager. It needs a frequent change, okay? Here at the bottom tier, we happen to use this simulation methodology and the computer simulation engine. For this thing, and many of you probably not yet very familiar with, okay? It's actually, I will define this as an enhanced version of AON, enhanced CPM, or P6, or Cyclone, can put them all together. This is the next generation of process planning and scheduling. Okay? It has been used for a lot of concept proof, and even we can do rapid prototyping and try to implement on some real projects. The theoretical foundation work has been done almost 20 years ago and published on those AIC journals. But today, I will just talk about this kind of implementation of the framework in this application context. Okay, so the middle tier for this fabrication shop basically provides a drawing board. It's like a whiteboard just to map out all the activities, the layout, the resource use requirements for the fabrication shop. Okay, so that doesn't change often until the shop updates the technology and the configuration. Okay, so over the 10 years, 5 years time span, the same technology, this part remains intact. Okay, here just give you one example for the field splashing technology I just described. We could actually represent it very nicely in STISA to account for all the logical constraints. Okay. At the top tier basically is an interface for the shop manager to specify attributes of girders, to define the availability of resources, more important, the sequence of processing all those girders, all those bridges. Okay. This actually give you one quick glimpse. Okay. It can just very flexibly adjust the sequence, processing different girder lines, different bridges, and answer what if scenario type of questions by simulation. Okay. In this case study, and just show you a simple bridge and the 5 girder lines, and then the different sequences, different number of trades or resources available have been tested. Okay, so then we can actually quickly identify the best solution here in terms of duration, in terms of labor cost. Okay, but what's more important is actually when we look into the simulation results, it can give us insight about this problem. Okay, so on the top is a simulated bar chart for the trades, for the resource utilization. Actually, it looks a little bit messy, but this is the reality. This is why P6 doesn't help. Okay, but then we can actually simulate the bar chart for the detailed resource utilization and try to elaborate and then try to provide decision support for the workplace planning. So here's one example, the to-do list for the journeyman, the welder number 1. Okay, so it can be just minute by minute or hour by hour, and which girder, which bridge, and it's a very specific. Okay, and similarly, we can roll up the simulation results to provide decision support for the project manager. So in this slide, you just see the start-finish time for each individual girder. It will be presented to the client or to the the field crews who are preparing for installation. Okay. In conclusion, and I said the major contribution here is actually to facilitate the problem statement in a sufficient and practical manner, and by using STISA. But they said that this is beyond STISA. You can use some other simulation methodology. Even you can look at other related problems. No need to be structural steel fabrication. Okay. More important, I want to say, we have identified a very effective way for engineering, how to engage the industry in computing research and in talent training. Okay. In this acknowledgement slide, I really want to share with you the Alberta model, how we engage companies, industry partners, and train PhD students. Okay, so on the top, the NSERC representing the Canadian version of NSF, the federal funding organization. Okay, and then the Supreme Group is one of the largest steel fabricators in Canada. Okay, they provide funding, they provide in-kind support. And then, I also want pay attention to the two students, the PhD students, okay? They are being trained, or some haven't, already been hired. They have been hired by the company in their leadership role for R&D, okay? So here are some pictures. You can see it's actually how we engage the shop superintendent, how the students are embedded in the company in the fabrication shop, and actually the prototype has been utilized in the real world. Okay, so thank you for your attention. I think any questions you can ask me now or send me email later.